All right, so I see that part of my job is going to be keep you guys awake after lunch. Hopefully you get something to eat. And then just kind of go through this. We only have a half hour, so there's a ton of information to go through. It's very difficult to do these in 30 minutes. So, but let's see if I could, I'll do my best here. I spent more time trying to take one of my other pitches and trying to narrow down the scope than I did building it up. So we'll give it a shot here. But okay, so I'm going to go through. I have about 20 charts, so I should be okay. But let's go through these. By the way, this is a typical tile that we use for the OpenCAPI talks. The bottom row are, by the way, the what we call strategic members of the consortium. So it's kind of interesting. But the first 5 on the left-hand side started this ball rolling. So it was AMD, Google, IBM, Mellanox, and Micron that started getting this whole concept of getting this OpenCAPI thing on its own feet out in the industry. Of course, IBM was, this IBM's base technology, but everybody saw a lot of promise in this. And then NVIDIA, Western Digital, and Xilinx had jumped on the train shortly after. But the consortium, by the way, is only a little bit a year old. But let's get into the talk itself. So these are the topics I want to hit on with respect to OpenCAPI. I want to give you a little bit of a background industry. It's only one tile. It's not one slide. It's not much, but I want you to make sure that you understand where this is all coming from, because it really does matter, right? Why we did what we did. Where it's used, I'll talk about the technology itself. I'll give you the overview. This is just a lot of information. There's no way I could do this in 30 minutes. Our typical, quote-unquote, education package that we do with people the first time we meet them takes about an hour and a half to walk them through this. Like I said, I try to condense and get you the highlights of the technical aspect here. Demonstrations, I actually have a few demonstration slides on tagged along here. We actually have demos. We had demos since last year. And then I'll have to say a few words about the consortium where all the stuff is happening. That is the home. And one of the questions that I do get asked, and this will come up a little bit later, but it's like, well, that's interesting. Why is there an OpenCAPI consortium? Why isn't this just a thing, part of OpenPOWER Foundation or whatever? But I'll touch on that. Now, something I did here, because I knew I only had 30 minutes, I decided to put a list of takeaways. And what I wanted to do was make sure that, if anything, when you leave this 30-minute session, these are things I want you to remember about OpenCAPI. I try to put down the key, value proposition of OpenCAPI. It is an open standard, an open I/O standard. By the way, you've probably heard of Gen Z, you've probably heard of CCIX, of course PCIe. But this is an open I/O standard just like the rest of those guys. But this is a high-performance standard, right? Those looking to do some serious performance work are the ones that are looking at this thing. All right, there's no, and the beauty of this thing, and this is the takeaway, there's no OS, no firmware overhead, anything involved with OpenCAPI. It bypasses that. This is one of the reasons why our latency is so low. I'll explain a little bit out of it later. And of course, it's got high bandwidth. By the way, it's not a power thing. This can work with ARM, it can work with x86, it can work with power, it can work with anything. So this is probably the biggest reason why we're not a part of the OpenPOWER Foundation. All right? We've had discussions and continue to have discussions with the other guys, the other architects. But this is something that's not tied to power. And this is why it stands on its own 2 feet. Okay? That's a very important thing to know. Let's see. I call this very low accelerator design overhead. I'll give an example a little bit later on, but I'll spill the beans now. We talk about how much logic design has to go onto the accelerator itself in order to be an OpenCAPI compliant thing. And in case of, we actually did a benchmark. We took one of the Xilinx FPGAs and we actually did some work on it. It was less than 5%, guys, that go on an FPGA. So it's a small overhead that goes on these accelerators to be able to be OpenCAPI enabled. Programming ease, I'll talk a little bit about that a little bit later. It's ideal for accelerated computing and storage class memory. Storage class memory, keep your eyes on this space. This is going to make data centers change. You're going to see the economics of data centers change. You're going to see a lot that's going to go on. That's why there's been so much focus on this place, right, on that space, is the storage class memory. So this is ideal for that because it is agnostic, like I said, but it'll also support ongoing generations of this new memory technologies, which is kind of the beauty of this thing built in. It also supports a heterogeneous environment. So not only does the storage class memory it does all your accelerators and all these different form factors, GPUs, ASICs, whatever you got going on there, right? So in that regard, it does, you know, networking, et cetera, and I'll talk a little bit more about that. It is optimized within a single system, and I'll show a little bit picture. In fact, I think it might be the next picture where it's used. But we took all that engineering and learning in terms of latency, reduction, bandwidth, et cetera, but we wanted to optimize performance within the system node. Okay, there's some that want to optimize themselves across the full data center. The problem is when you start doing that, you're definitely making some big trade-offs. All right, we did not want to make that trade-off. We wanted to go after the performance where we thought it needed to be, and we stuck within the box itself more or less. So it is optimized for that. And the biggest thing, this is not a paper tiger. There's products out there today with OpenCAPI. They exist. All right, we got. And I think, by the way, if you haven't, stop by the booth. You'll see, you know, the Alpha Data, Mellanox, and there's, you know, there's other emerging things now. They got prototypes of the tables from Mellanox. I'm not sorry, from Molex and the others. So if you haven't stopped by, feel free to stop by the booth and just check it out. This stuff is, like I said, this is not a specification in flight. This is something that exists today, and they're building stuff today. All right, that's important to know. So those are, I think, if I had to net out what are the key takeaways, and you're going to hear some of these themes over and over as I go through this thing. That's why I felt it's just important just to put it out there. All right. Okay, let's talk about this industry chart. Now, you know, as long as I think any of us have been in this industry, you know, the growth for computational needs has never slowed down. It's just getting more and more and more, right? Well, you know, these emerging workloads, right? You hear about artificial intelligence, you know, deep learning and all this stuff. This is driving a ton of, you know, data analytics. This is driving a ton of computational information that, or the capability that needs to exist. But, here's the big but. We used to do this all the time. IBM was big into this too at one point, right? You take a silicon chip, processor, remap it, boom, there's your 2x, whatever it is, you know, cost, price, performance, whatever, right? Silicon technology ruled the battlefield at the time. That's gone away. That doesn't exist anymore. Anytime a company does invest in silicon technology, they look really hard how fast they roll that out. You'll get density, of course, and some other benefits. But, you know, the huge benefit we used to have years ago by remapping a prior silicon chip into a new technology, it's not there anymore, guys, other than density. So this is a big deal. But now you got the other side of the equation that says, but I need more. I need more. So how are we going to satisfy that? Well, that's what's driving this whole thing of this hardware acceleration. I mean, IBM saw this back in Power 8 in 2013. That's why we introduced this first concept of CAPI 1. I mean, acceleration, we knew that Moore's Law is kind of dead, but it's not dead, right? From a silicon point of view, it's dead, but but stay on that curve because you need compute power, it's not dead. So this is the way we saw it was going to roll out. And it is rolling out this way. The hyperscale guys and the data centers and the high performance guys that need the higher network bandwidth, you got deep learning and HPC going on with the higher bandwidth needed for accelerators and memory. And as I mentioned, this emerging memory technology, they're starved for bandwidth and low latency, especially if you have these huge gobs of memory, storage class memory, right next to a processor. It's going to want this latency low, right? And that's critical. So, you know, these accelerators, these workloads that are driving these accelerators essentially now driving what do we need? Because if you're going to use accelerators, you're going to have to get stuff in and stuff out fast, right? And it's got to be huge chunks of it. So if you're going to use these things, you're going to have the bus to support it. And these accelerators essentially defining the characteristics of what that bus needs to look like. So now we're getting to the point that I made a little bit earlier. Why did OpenCAPI come about? Why is it here? These are the driving factors that are making this thing come to be, or that made it come to be. All right? So you have this growing demand for network performance and network offload, we call it. You got coherency that's playing for the game. If you're going to put all this gobs, especially of memory and these accelerators, everybody's going to want to start sharing memory because the accelerators come with a whole vast amount of memory too. So the host and these accelerators now want to start talking to each other and start sharing their memory. So coherency is creeping into the space here. And like I said, you got the storage class memory stuff. And by the way, one thing that we've learned, and I wasn't quite there yet. It was like, geez, I don't know, maybe it was about 3 months ago. And I kind of had this gut, but now I believe it. There's no one form factor that's going to fit everybody's purpose here. This stuff is going to constantly evolve. You're going to see FPGAs are going to satisfy a requirement, GPUs are going to satisfy certain requirements, ASICs are going to satisfy certain requirements. Not one's going to rise above them all and say, this is the answer, this is what everybody's going to use. It's all about choice, because depending where you are in your development cycles, what you're doing, any one of those things is going to come out is the winner for what you want to do. So you need a bus. Once again, it's going to be flexible to take these kind of things. It almost sounds too good to be true, right? But all this stuff is relevant to these modern data centers, is what I'm talking about. And that's why when this thing started, by the way, like I said, we're a little over a year old, basically, the technology. But we had this vast forum that just says, okay, this is something that we could be interested in. Especially the cloud deployment and hyperscale guys. That's why they're looking very close at this thing. And in fact, some guys took the next step. By the way, I don't know if you guys were in the, if you were in the talk with the keynote speakers this morning. Yeah, so you saw what Google announced today. Google announced, right? So they deployed Zeus, and Zeus is Power 9 that has that OpenCAPI technology capability. Okay, so where do we want to use this thing? Well, it's kind of neat because you use this about anywhere. And when I say heterogeneous, it does all these things. If you got accelerators, take a GPU, FPGA, whatever. By the way, these slides will go public, I'm pretty sure. So if you take pictures, I was just going to say, you take pictures, go for it. But I think they're going to post all this stuff out live. But it's not confidential. If you want a copy, I'm happy to send you a copy. So none of this is confidential. In fact, we stopped by the booth. A lot of these charts are in the booth, too. So anything from accelerators, you know, coherent network controllers, or your advanced, your storage class memory stuff, right? Your network controllers, it's got all of this. But the interesting thing is, we did it all on this peripheral there, all of this stuff, right? And we started talking about, well, how about the standard DRAM? Now, one thing you have to understand is IBM has had decades of engineering effort going into attaching DRAM and microprocessors, obviously, right? So we took this spec and we took it one step further. We took all the learning that we've done, right, on doing classic DRAM technology interfacing to our processors. We applied all that engineering and we came up with a spec called 3.1. And the latency on this thing is incredibly low. I mean, I'll brag. I'll be proud of this one. Actually, if the guys from the team were here, they'd be bragging too. But this 3.1 took all those decades of learning and took the latency even a little bit further and down to reduce it. So now you can take your classic DRAM memory, and we have this bus called 3.1. It'll do that too. So the intent here was we wanted to insert a buffer chip, a memory buffer chip, okay? It's not on Power 9. Our next processor is going to have it. It's the follow-on to Power 9. We'll have this buffer chip capability. And I'll have that 3.1 spec on that processor. And we added this because, first off, it gives you capability. By putting a buffer there, you could put more DIMMs behind that buffer, so now you have more DRAM right by the processor. But the beauty of this thing is the added latency, because of that buffer chip, you're a single-digit nanoseconds, 5 nanoseconds, right? So it's tiny. So you don't even see it. So that's the engineering that went behind this 3.1 spec, and that's what all the learning went behind it to do that. So that's round trip, by the way. Okay, so now what's neat about this is, and we took the step, we said, you go on that OpenCAPI website, that www.opencapi.org, you can actually download these specs, the TL, the DL, the 3.1, 3.0. You can see those specs. All you gotta do is register, put your name or email or whatever, and you can download this thing. Now, I will tell you that these are not the final specs. Those specs that are posted on our website were the ones that IBM contributed to the consortium, but it gives you certainly a very good flavor, a good idea of what these specs are about. So, feel free, go ahead down and take a look at those things, right? Now, if you want the latest and greatest, and there have been changes to the specs, obviously, the work groups that are taking these specs and updating them, et cetera, those are within the work groups themselves. But eventually they'll go live. But all that work's going on in the consortium itself. So that's where we use it. It's virtually, when we said heterogeneous, we meant it. You could use it just about everywhere, right? And all these benefits I'm talking about they all apply. There's nothing here that rules any of these benefits out because one case versus the other. All right. Let's talk about some of the key attributes. So as I mentioned a little bit earlier, this is an agnostic bus. It's not tied to a specific architecture. Any architecture could pick it up, all right? It is optimized for high bandwidth and low latency. There's been a lot of engineering behind that to make that happen. This is important. It has its own PHY that runs at 25 gigabit per second. It's not running over PCIe, you know, Gen 3, even Gen 4, that's even 16 gigabit per second. This is running over 25 gigabit bus. Now, you've probably heard about the NVLink 2. That's a proprietary bus that exists between IBM and NVIDIA for the NVIDIA GPUs and the IBM systems. Think of this OpenCAPI thing as like kind of like the open version of this, more or less, right? But I would say plus, okay? So, it uses that 25 gig link, that 25 gigabit PHY, all right? Coherency, I talked a little bit about that. As coherency starts to play a more of a role as you attach these accelerators, a lot of the hosts to accelerate to the devices to host, that's going to be becoming more interesting. Virtual addressing is used in OpenCAPI. So we use virtual addressing. It's got very low head. This is what enables to keep all that code crap out of there, right? It doesn't slow us down. So we avoid all that nonsense by leaving those guys by the side of the highway, and we just go. So virtual addressing plays a big role here, and I have a separate chart on some of the added advantages of virtual addressing. And I mentioned a little bit earlier, there's a wide use of use cases here. There's the CPU coherency to the device itself, the home agent memory submerging. Is architected for both, and I mentioned this classic memory and this emerging storage class memory. So of course it does both. That's the difference between that 3.1 and that 3.0 spec. And as I mentioned earlier, also, it has this minimal design. So when you make this accelerator, the amount of logic you put on this accelerator, it's not a big tax. So whoever's designing these accelerators, so you know, if it's, so you drop by the table, you can see the Mellanox card, the Alpha Data card, whatever, but if whatever logic's got to go in at FPGA, it's so, you know, you're not going to even know it's there, like 5% or less. So that's another big advantage, right? Trying to make the guys who designed the accelerators, we're trying to make it easy for you guys. We're trying to make the coding easy, we're trying to make the design easy. All right, part of that was, what's that? Yeah, well, CAPI Snap, well, that's the highway to get you there, no doubt. But just the amount of work. I'm sorry, go ahead.
Yeah, I have a question. Do we have a vendor who is going to produce an Ethernet card for low latency launcher that would be equivalent to what solar equipment is?
Good question. I will say that there's work underway. There's certainly discussions underway. It's too early to say at this point. But I was going to ask what company you represent, but there's a gentleman in our
I'm from IBM, but I'm talking about selling directly to like the high frequency trading.
Absolutely.
market.
So you know Shaki Kapoor?
Oh, no, very well.
Okay, all right. He's the one that's having those conversations. Right. And right now I couldn't say yes, no. But I will tell you, because of this, the interest just went off, it took off. This is, Power 8, we started these conversations, in fact, I was shouting Shaki, we did a lot of Chicago meetings, a lot of Manhattan meetings with the high-speed traders, and the latency just wasn't quite there.
Exactly.
I'm going to show you a chart a little bit later in this deck. You're going to say, wow, we are not only there, we're beyond there.
And that was using the standard Mellanox Ethernet adapter?
No, yeah. We didn't do that. It was a, how do I say this? It was a simple test that we did. So we didn't latency.
Everything we have today is there's iLinks FPGAs, but it has extremely good latency. So some of these, some of the people we talked to have FPGAs. But as far as native OpenCAPI, that's the future thing, like a hardware-enabled OpenCAPI.
Right.
We'll have better, we'll have very good latency.
Yeah, but the issue is if you're going to compete in that space against Intel, you can't just be better, it's got to be better.
Well, yeah.
Clearly, yeah. Agree. That's why on Power 8 we weren't. Power 9 is a different story. So yeah. But hang in there with me. Let's see. Yikes. Okay, we're running out of time here, guys. Okay, have to pick up the pace here. All right, IBM has always had this strong family of I/O, right? So we're leading the pack with Gen 4, PCI Gen 4. Get rid of that. NVLink 2, we have that. And then, of course, the OpenCAPI. But what we did was, this is kind of depicting the die's capability in Power 9, right? We got 48 lanes for PCI Gen 4, and you could bounce between Gen 3, Gen 4. And then we have 48 lanes dedicated for that 25 gigabit link that I was telling you about. That either could be NVIDIA 2 link or NVLink or the OpenCAPI link, right? So let me keep going here. So now I'm going to, and I apologize, again, it's only 25 after, wow. So on the virtual addressing, we operate in a virtual address space. Eliminates, like I said, the software overhead, right, to get the latency down to the lowest. It runs without the kernel interference, simplifies the programming, which is a nice thing, and of course, it improves the overall accelerator performance. All the virtual, address translation, virtual physical address translation occurs in the host CPU. We take that burden off the guys who are creating these accelerators, so that's done on the processor side. Reduces that design complexity on the accelerator. Ensures more the interoperability between the devices. And security. I mean, security has been a big buzzword lately in the industry. The added benefit of having the virtual addressing is nobody can get direct access to from your attached devices into your hosts. So that kind of shields any kind of concerns there. So I'm going to just kind of race through this here a little bit. So here's some of the paradigms or some of the acceleration things that you can come up with, right? So we have the basic, offloading, which is typical accelerators. You have egress and ingress, so the information goes in and out of the accelerators. You can operate on that data real time. It's really interesting. A lot of the government stuff, especially looking for terrorist activity, those kinds of things on the internet. Some of these things play very well in that space, right? I know a lot of countries are doing like pornography checks and things like this. So egress and ingress is something like that. There's an approach called needle in a haystack engine, where you just got to go out and find something, this huge data place. And then you've got stuff that you can do both way, obviously, right? So, the whole architecture of the OpenCAPI does well in this space. And now let's talk about the memory. I'm going to touch a little bit about the memory piece of this thing. Now you've got a common interface for the memory between non-memory and memory devices, right? So as I mentioned, CAPI 3.0 could be used just about anywhere. Extreme bandwidth for DDR, as I mentioned, you could have right into the memory interface. This is for the buffer chip capability. It's agnostic, so as this emerging memory technology continues to emerge with new technologies coming out, this bus will be able to handle it because it is agnostic, and it separates the buffer from the raw host. Okay, optimize your cost performance. Here's just examples, and I think we touched on all these. But one I didn't touch was tiered memory. You could have a tiered memory approach now, where you could have some nearby your classic memory DDR, but then you could have storage class memory beyond that. There's a lot of interest in some of the large data center guys who've been looking at this too. All right. Okay, performance. I had 2 slides of performance. So now let's talk about performance, right? First one's performance and bandwidth measurements that we've done. The other piece is latency part, which would be interesting that you're looking at. So we did on CAPI 8, you had CAPI 1, so that's tied to Power 8, and then CAPI 2 and OpenCAPI 3.0 is on Power 9, all right? And that's the specific Xilinx FPGA that we use. These are the actual bandwidths that we measured. So on Power 8, when we introduced this on that CAPI 1, we ran it over that PCIe, right? So obviously, you're going to have limited bandwidth on a Gen 3 interface. But then we took it on to Gen 4 interface. We introduced it on Power 9. Of course, it's gotten better. But then when we ran this on Power 9 with the OpenCAPI interface, the bandwidth, of course, significantly improves, right? So
OpenCAPI 3.0 available now?
on Power 9.
Oh, it is?
Yeah. Okay. Now, that's performance. Now, if you look at latency, right, I know this is a busy chart. Now this is stuff that we did in our lab. This has gone through our legal review like 10 times because we're showing Intel data here now, right? So they scrutinized the heck out of us, but we had to stand tall and make sure that this stuff is real. But I want you to focus on this piece here because there's all these conditions. But you start off with Power 9. You got OpenCAPI and Gen 4. Of course, you got Gen 3 as a benchmark of what Gen 3 looks like on Power 9. But then on the right-hand side, we did the Intel with Gen 3. If you look at the top latencies, it gives you a rough idea. The frequencies that you see is your core frequency. So you see that 3.9, 3.9 They're all equalized to the same port frequency. Then you have the 2.4, that's non-core. You call it, that's an IBM. Other people call it the rest of the chip. But that's the latency that we got. 378 nanoseconds in that range versus the 700 some. So when you ask the question, is it better? Yeah, we got past that point now. And this chart is the first time we've shown this chart in the industry today. We've been holding this off to the side. So I think Brad McCready is going to show it, if he hasn't shown it already today. I'm showing it today, and this will be shown in Open Compute tomorrow. So in fact, I got to leave tomorrow morning for Open Compute, but this is the first time we're showing this chart, guys.
Is that on any specific model?
Yes, it is very specific.
Yeah.
When you get the slides, you could check out the exact system, et cetera. Okay? So I want to make that clear. We've done enough benchmarking now that we're pretty bullish about this thing.
What's the transaction size?
It's a simple test. This is a simple test that we ran. That's all we wanted to do is just, get something out there that says, okay, what does it look like? To do an apples-to-apples compare, right? So nothing too complicated, but just to create the traffic.
It's small packets, kind of huge volume. So that's what kills the other. Well, big packets, we get a higher sustained bandwidth too. So,
Yeah.
well, if you think about it, if you transfer a big block, it's tremendously longer on an Intel system, but it's only Gen 3 PCIe.
The difference will carry over, if that's what you're asking. Okay, so here's two examples of some of the cards that we have that are OpenCAPI enabled. We got the Mellanox. Oops, that just ran on its own. That's strange. Okay, so what's going to happen here? Oh, what happened? That's strange. Okay, typical eye diagram at the bottom. That's our 25 gig bus that we've been using. So that just shows you. And we've done so many of these measurements, but these eyes are very clean at 25 gigabit per second. And so what we did was I only put 2 demos here, but what I wanted to show was that this is hardware that exists, right? We wanted to make sure that it was clear that what's going on here. Come on, man. Huh. There you go. Oh, that's strange. All right. Trigger mechanism was in there. So the bottom right-hand side, you can see how many gigabytes per second that's running. So it's like shy of 18, which is pretty much near our theoretical point that we figured it would be coming at. So we're very happy with this. We ran this. I only have 2 slides in here. This thing is like 17 gigabyte, whatever. This is a huge file. At the table, I show a number of demos over different systems. There we have a Mihawk system from Wistron. We have a Lanyang system from Inventec. We have the Barrelite G2 system. We have Google's Zeta system. We have IBM's Newell system. We ran all these demos on these systems, and you can see it at our booth. I only took 2 here because the thing was just so large. And this thing is like a mind of its own. Okay, so what I wanted to do was, it was hard to see in the diagrams, but I tried to draw a little yellow circle where the card was in the picture to show this wasn't something that we made up. And I think over here too, that's the alpha data card there in the system when we did the demo there. Oh, there you go. Now that one's working there. Okay, so let me keep going here. Let me talk a little bit about the consortium here. And I'll probably pass the point now where it's 1:32. Here's the consortium. I just want to say it was started back with AMD, Google, IBM, Mellanox, and Micron. When we started this thing, today we have over 35 members. We have like 5 more in the queue. A lot of universities are starting to get interest now. UCLA we had a ping from them. They want to join. We got one from university out in India. We had, so you can look at the current members. I'll get there in a second. So we're well established. We've got a functioning, technical steering committee. We've got, all our legal stuff's in place. We got our marketing, communications. The work groups is where all the activity is. We have a TL specification work group, a DL specification work group, PHY signaling, PHY mechanical. We broke those up because now we're seeing interest not only with the, these cables, the optical guys are coming in and say, okay, I want to know how the optical is going to play in this space. So that's why we have our own, signaling there. And the mechanical compliance and enablement. Enablement's a big deal, and I'll tell you a little bit more about that. A second is a chart that shows what we've got available today. We're in the process of looking at the memory, software, and accelerator work groups. So we're looking at those, get them ready. I mentioned the OpenCAPI spec is on site. It's the one that IBM contributed. You can look at it today if you want to knock yourself out. like 130 pages on the TL, and it's like, I don't know how many pages on the DL, it's less, but you know, I encourage you to still take a look at that thing. Design enablement. This is what you get today. This stuff exists today. So if you want to go build an accelerator card, you want to do an FPGA, whatever it is, this stuff exists today, you can get it, right? So you join the consortium, it's all yours. And so the one thing that's hanging out, I think, in fact, I think the reference drivers are going to become available shortly. The reference card design, we were hoping to get that out this quarter, but that slipped into next quarter. I think it's going to be early second quarter. So all this stuff exists today if you want to do the accelerator. This is the different membership levels. You know, the lowest is 5K. We wanted to get something in there that just like PCI, you know, PCI, the SIG, and others, we wanted to be in that space. Current members today, I kind of depict a little bit this way here. So you've got your accelerator solutions on the right-hand side. You get your software and systems in the middle, deployment, and then you get the research, and now you get universities starting to get interest here, and they're starting to join over there, and that's starting to build up. So the message here is, you know, certainly, right, I encourage you guys to join us. It's, like I said, the minimal level is only 5K a year, but you have access to a ton of information, and, you know, including all the specs and all the enablement, et cetera, and you can participate in these work groups that are creating these specs. And if you haven't, stop by the booth. I'm hanging out there so we can talk a little bit more about this. All right? I apologize. It's already, I know I tried to cram in here. It's 1:35. I've already passed my limit here, guys. Okay. We'll take, what, any one question? 2 questions? Are the speakers for the next topic here? Okay. You're going to go up next. Okay. All right, folks, thanks. And I'm around, so I'll be here all day, so stop by, see me. By the way, I'll introduce Jeff Stukley in the back room who was talking, answering questions earlier. Jeff is one of the architects in IBM that actually contributed to the creation of the spec. So if you really want to go down deep and dirty, Jeff would certainly be able to answer just about any question that you have also. And he's hanging around the booth and the show too, yeah. All right, thanks everybody. Appreciate your interest.